Hello, Algebra 2. Alright, so I'm going to go over Chapter 6, Section 6. Normally, this section I would have handed out a worksheet to start the notes, like before the notes began. I would have given the whole class a worksheet, and then we would have worked through this worksheet together. It wouldn't have been homework, it would have been classwork that we did together. And we would have filled out the blanks. Anything you see handwritten here would be a blank, and we would fill this out together. Um, but I'm just going to go through the already filled out version of this worksheet, just because that'll be, given the situation, that'll be the easiest. That'll be the easiest to do at this point, I think, as far as me recording videos and whatnot. Before I actually begin, I'm going to jump back to notes that we took BC before coronavirus. And you might remember this compound interest formula. This compound interest formula was, let me just recap this. This would give you the total amount of an investment, given that we plug in the principal, the starting amount, the interest rate in decimal form, the number of times it's compounded per year, and the number of years the investment is. Okay, so we would plug all those in and we would be able to find the return on an investment given all that information. Okay, and we did some problems with that before. Well, we're gonna go back to that for this worksheet, but we're gonna simplify things a little. Okay, let's make this as simple as possible. Focusing in on just compounding, we're gonna experiment with compounding it. How many times we compound it in a year, and that's what we're going to experiment on. So we're going to make everything else as simple as possible. Let's start by investing $1. That makes that pretty easy, right? 1 is an easy number to deal with when we're dealing with multiplication. So we're investing $1. The easiest interest rate to deal with would be 100%, because that translates in decimal form as 1. 50% is 0.5. 100% is 1. Double that. Okay. The easiest time to deal with is 1 year. So we're pretty much plugging 1 in for everything and just focusing in on the n. Okay, we're going to deal with the n. So we can use our graphing calculator, which, let me get that up here and positioned. Oh, I need to load it up. Sorry. Not prepared for the, oh. Not mean to grab the wrong window. Sorry about that. Okay. All right. So now this is over here. I realize my little video of me is going to block that. The buttons, but I don't think that you need to see me actually push the buttons. I think you can just see what the calculator gives us. Okay, so actually let's not show too much of that too quickly. All right, so we're going to do an investment of $1, compounded 100% for 1 year, compounded once per year. Okay, that's what's going on here. And so the situation would be, if you were earning 100% interest on something, like no bank would ever give that, but that would mean you're doubling your interest. So you're taking everything you had in there, and you're going to get 100% of that again after 1 year, and that would double it. So $1 would go to $2, and that makes sense that would happen because 100% interest is doubling. Compounded once would happen once. And also, if you look at this, you're going to have 1 times 1 plus 1 over 1. 1 over 1 is going to go to 1. Okay, 1 plus 1 would be 1. It would be 2. 2 to the first power is 2 times 2 is 2. So we get 2 from that. But on my graphing calculator, I'm going to actually do something where I'm going to put 1 in the graph y equals area. I'm going to put 1 times, and I'm going to do 1 divided by x. Oops, sorry. 1 times 1 plus 1 divided by x, n paren raised to the x. Okay, so I'm plugging this in the y equals 1. Okay, and I'm doing that because I'm going to use a little bit of a thing that the calculator can give you. This is a pro tip for your calculator. Now, I put x in because the graphing calculator likes x in the y equals area, but that my x is just my n. All right, then so I put that all in the y equals. Okay, I'm gonna quit out. I'm gonna actually turn my camera. Where's the camera? There we go. So you don't see me right now, but you can still hear me. So that's in my y equals. Okay, so I'm gonna quit out of that. So now I'm back at the home screen, and that's still in my y equals. I'm gonna go into vars. You can rewatch this if I go too quick. I'm going to go over to y vars. Okay, vars, y vars. I'm going to click on function. I'm going to click on the first one here, y1, and then in parentheses I'm going to put 1 behind it. Okay. And what I just did was I called on whatever is in y1 in here, and with the parentheses I'm plugging 1 in for the x values. Okay, so this is saying plug 1 into whatever x values are in y1. And so it's plugging 1 in here and plugging 1 in here. Okay, so this would be equivalent to me typing up 1 times 1 plus 1 divided by 1 to the first power. Okay, and hit enter, I get 2. Well, now instead of typing that up every time, or even doing second entry every time and then going through and paging through and changing my n values is what I want to do, I can just do the y. I can do the y vars, this thing here, and change this value here once. And it'll change, and that's deciding what's going in for these x values in here. So this is a pro tip of the calculator. So now I'm going to plug in. So first I started over with plugging 1 in because I wanted to compound once per year. Now I'm going to compound twice in 1 year. Okay, so rather than going to this and then, well, retyping it would be the worst case. I could go to this and page through this and change these to 2, and I get 2.25. That's correct, but it's instead of doing all that, I can go grab this again and just page over and change this one thing to 2 and get 2.25 because it's taking this 2, it's plugging it in here and here, and it's giving me the same thing as this. Hopefully that makes sense. And so then I can just zoom through this. This is the idea. And I can just zoom through all these and plug in values and see what I get for the value. So what this is here is this is semi-annually. So going back, now that I'm done, hopefully you understand how I'm using the calculator to get these values. So going back to what I'm actually doing here is I'm taking $1 investment. I'm getting 100% insurance, which is not something you'll ever get in a bank. But this is essentially you're going to double your investment at 100% what compounding once per year. Well, what's happening is I'm getting this. I've been having it compounded twice. Okay, so when you have any type of interest rate that's happening more than once per year, you do that. You're doing the part of the percentage each time it's compounded. So halfway through the year, you're doing a 50% interest increase on the investment of $1. So halfway through the year, I'd actually have 150 because I'm doing an increase of 50%. Okay, so 50% of $1 is 50 cents. I don't know that I need to do the multiplication. So I'm going to have 150. Okay, and then I'm going to have that again. I'm going to do that again. I'm going to do an increase of 50%, and the 50% of 150 is 75 cents. So I'm going to do an increase of 50 cents halfway through the year, and then I'm going to do an increase of 75 cents the second half of the year, and that adds up. I have $1 plus an increase of 50 cents. That's 50% of $1, and then I do another 50% of now $1.50, and I get a 75 that I just showed you how you get, and you get to 225. So what happens when you're doing interest divided over a year? You're doing you're going to divide the interest rate by the number of times it compounds and do each of those parts each time. So that's why I'm doing 50 and then 50 because it's compounded twice. So it's 100% over the entire year, 50% at the halfway point and another 50% at the end, but you're going to gain interest on what was already compounded earlier when you compound again, giving you 225. So that's why it's more, okay? So let's do it 4 times. We're going to do it 4 times. And so this is where it's going to get increasingly more difficult to type this up, and then you're going to get all these decimals, so it's just a lot easier to do this. So we're doing 1 over 1/4 to the 4th power. You're going to get $2.44 because now you're taking you're going to take the 100%. It's going to be 25, 25, 25, 25, but the second 25 is going to gain interest on the amount of money that you made from the first 25, and the third 25 is going to gain even more because of the interest that you earned earlier. So it's just going to continue to build on the interest. Okay. Monthly is 12 times, so I'm going to do second enter to bring that up and type 12 in, hit enter. You're going to get $2.61. I'm actually going to bring the camera back in because I don't think you need to see the buttons being pressed anymore because it's going to just be redundant now. I'm doing second enter over and over again. So the next one is daily. What if you earn interest daily? Second enter. I'm going to do 365 times that you're earning interest. Every day you're taking 365 365th part of 100%. You're compounding that interest, and then you're going to continue to do that every day. You're getting $2.71 at the end of the entire year. Okay. All right. So what if you're doing it hourly? Every hour you're compounding the interest. Okay. And again, I'm going to just confirm that the numbers I've written down are correct as you can see them there. So every hour is compounding the interest. Okay. Every hour. It's going to take the interest rate and it's going to continue to just find the current interest rate, add it to the principal or the amount of money in the bank, and then it's going to do it. The next hour it's going to do it. It's going to continually do it. Well, you would get at the end of 1 year $2 if you invested $1, $2.72. This would round up to 72 cents. But I'm going to show a lot more decimal places. I'm going to show all the calculated decimal places actually. What about every minute? Oh, by the way, there's 8,760 hours in a year. 20, 30, 36 times 24 on a normal year. That's where I got that number. Well, now I'm going to take that times 60 because there's 60 minutes in every hour, and there are over half a million minutes in a year. Okay. Okay, so there's 8,760 hours in a year. There's 525,600 minutes in a year. Okay, and so I'm going to then, and this is where it's really nice to use this thing instead of the trying to type these numbers in. So 525,600. So notice how this doesn't change that much. It does change a little at the end there. What about every second? Again, it's not changing much. Every second, if it compounded interest every second. So this is how many seconds are in a year. 31,536,000. And again, 2.718. Okay, so it seems to be leveling off at 2.718. And that's because if we could even go further, right? You could even do half a second, 1/10 of a second. You could keep going. And this actually is getting closer and closer to an irrational number, similar to pi in that it's irrational, and similar to pi in that it's used a lot. Now, it's not used a lot in geometry, but it is used a lot in upper level math, and that is the number e. Okay, the number e is the number that is the irrational number that if you had invested if you had an investment that was compounded compounding continuously, like every moment it's compounding, it would grow at this rate, okay? Compounding 100%, compounding continuously. Essentially, that's what we're getting closer and closer to, compounding continuously, okay? And if we kept going, it would get closer and closer to this number e, which does not repeat. I know there's a lot of 8s and 2s there, but it actually doesn't repeat if you look at it closer. It doesn't keep on doing that or anything. So the number e is an irrational number. It's called the natural number, and it actually, we're going to use it in logs and we're going to call that the natural log. Okay. There's one other question. Describe the behavior that I would have you fill this out, but describe the behavior of the sequence, and the value column approaches 2.718. Okay, so it's just getting closer and closer to this 2.718, which is the natural log. So now I'm going to go to the actual notes, okay? And this is what we just discovered, that as n becomes very large, this thing here that we just did, the compounding interest formula, approaches this number, which we call e, the number e, okay? And I maybe did it a little fast, and actually you probably couldn't see it because of the window. Sorry about that. My video. E is on your calculator above the division sign. If you do second division, that's E. It's right under the pi. Second exponent symbol is pi. There the E button is. Okay. So E is irrational, does not repeat, does not terminate. So this gives us the natural exponent function, an exponential function with base e. So this is a number, so just think of this as like 2 to the x. F of x equals e to the x is called the natural exponential function, natural exponent. So we're going to just do some simple evaluation of this. Evaluate f of x equal to e to the x for x equal to 2, x equal 1/2, and x equal to -1. Okay, so if x is equal to 2, e squared, and e squared is, excuse me, we do second e raised to the power of 2. Just using this e button on your calculator. Okay, that's where the 7.389 comes from. E to the 1/2. So, oops, sorry. Second e raised to the 1 divided by 2. Enter. This would be the same as the square root of e, right? You don't have to write the square root of e, but the power of 1/2 is the same as square root of e. And then to the -1, e to the -1 would be second e raised to the -1 power. This would be the same as 1 divided by e to the first power, just e. Okay. This is just helping you use the e button on your calculator a little. Okay. Let me bring back my video. So there's a continuously compounding formula where we're going to actually replace a lot of the stuff in the compounding formula we're going to replace it with an e, because a lot of that stuff went to e. That's what we showed with that worksheet. So if you are investing, let's just say dollars, into an investment that's compounded continuously, then the amount that's given back of the investment would be the principal. The principal is still the number of dollars invested, then number e raised to the rate, the interest rate, then that would be in decimal form times the number of time in years. Okay, and that's a continuously compounded formula. So investments at a bank won't do this, but if you consider other investments, you can consider them continuously in compounding, because like an investment in a house, or what else do people invest in? Property is the only thing that's coming to mind right now. I was going to say cars, but cars are bad investments unless they're antiques. Most of those don't accrue interest. But let's just say we had an investment that is continuously compounded, and it's $1,000, and the interest rate is 7.6%. So this is a normal interest rate, but instead of it being compounded regularly like at a bank in a bank account, they're going to say, okay, this is the end of the month. Let's compound your interest, add it to your account. Well, other investments, they just you buy it and you sell it for more. So it's kind of it's just always gaining interest or losing interest. So it's always compounding continuously. Um, so but this problem here, let's just treat this like kind of like a bank situation, like there isn't a bank, or let's treat it like let's say there's some fictional bank out there that's compounding continuously. No banks do that. Or this is $1,000 investment, and so if the interest rate is 7.6%, and we're going to invest it for 8 years, so we're going to first compound it quarterly and then compound it continuously. Okay. So remember to change 7.6 into decimal form, move it over twice. Our principal is 1,000. Our time is 8 years. To do this quarterly, we're going back to the equation, the compounding interest formula that I used at the beginning. N is equal to 4 because it's compounded quarterly, 4 times a year. So if we plug in the values, P is 1,000, our interest rate in decimal form, divided by 4 to the power of 4, which is the number of times it's compounded again, times 8 years, and then we evaluate, take that division, multiply 4 times 8, get 32, add those together, and you get $1,826.31. Okay, pretty good return after 8 years. That's pretty high interest for a bank account. If this was compounded continuously, though, we would plug it into this formula. Principal times e, the number e raised to the power of r times t. This is a number, okay? So we would take 1,000 times e, and then 0.076 times 8, which if you take that on your calculator, so 0.0, this is how you do it. I know I'm blocking, my screen's blocking it. So that's where I got to 0.68, and then and then to do e, so I'm going to do e, second e, raised to the power of let me put 0 in, 0.60, oops, don't put 2 points in the number. Okay, there we go. Okay, so I get that value that I want to then multiply by 1,000. Make sure you do order of operations, exponents first. And I will get $1,836.75. So you can see how you get more. It's not a whole lot more, but it's compounding continuously. And it is more, okay? And that's actually it for this set of notes. There is a part 2 to this. I don't know if this will be released in 1 week or 2 weeks. I haven't decided that yet, but I'm definitely going to cut this video off here. But I don't know if I'm going to have these notes cover yeah, I think I'm going to have these notes cover 2 weeks. So this will be the 1 week, and there'll be some book work. And again, I might have flashed that real quick there, but don't go by what I wrote in the notes yet. Go by what I say in the Google Classroom. I might change it because of the circumstances. And then so there'll be another section, a part 2 of chapter 6, section 6, and we'll go more into the number e in that. All right, thank you and good day.